A good analogy is music concerts. This guy right here is Andrea Bocelli. He's a opera singer. I went to a concert and sat in the very front row um, at the concert. So there was literally no shielding. I got the full effect of the music, the full effect of the speakers, the stage, and all of that. He's got a great voice. Google him if you've never heard of him. Okay, now if we want to go to a different concert, maybe Taylor Swift, for example. I've never been to a T Swift concert, but wouldn't mind going, I suppose. And whoever took this picture is kind of partially shielded, right? There's quite a few people in between the person and the stage, and so the music, the effect of the music, the speakers, the volume, all of those things are somewhat shielded by these other people that are in between the stage and the observer or the person taking the picture. If we look at another example, this is a bunch of people waiting for a Mumford & Sons concert. If we look at this guy right here, he is very, very shielded from the stage. There's a lot of people in between him, right? And it looks like it's a flat ground, so he probably can't really see the stage at all, which kind of explains why he's bored and looking at his cell phone. So if he was an electron and the stage is the nucleus, then the effect of the stage or the effect of the nucleus's pull is being kind of absorbed or kind of shielded by all these people in between him and the nucleus, or him and the stage, right? So this analogy kind of helps to understand why this happens, but it's a little off because it doesn't exactly describe how it happens. In the analogy, in the music concert analogy, these people are kind of absorbing or blocking the sound from the stage, but in an atom, it kind of acts a little bit differently, or kind of happens a little bit differently. So let's go back to the atom. Here's a zoomed in picture of an atom. Here we have the nucleus, which would be positive, and the negative electrons. Now, in the stage analogy, or in the music analogy, this attraction force is kind of absorbed or blocked by the other people in the concert, or in the auditorium. That's not really happening in an atom. This electron is still getting the full effect of the nucleus. It's the full attraction force. However, there are other forces at play. When you have electrons in between that outside electron and the nucleus, remember that all the electrons are negative, so they're going to repel each other constantly. So every electron is repelling every other electron. And so the total force, you could say, is decreased because you have these repulsion forces pushing back on the electron, and then you have the attraction force that is always there, always felt. If we want to look at two similar atoms, sodium and potassium, and there's also a picture of lithium here. These are all in group 1, I believe. And so they're very similar in reactivity, but potassium is more reactive than sodium. And the reason that this is the case is because of shielding. So if you look at these two electrons right here, which one is more shielded? There's a lot more electrons in between this electron and its nucleus than there are between this electron and its nucleus, right? There's a whole nother ring of electrons. And so this electron is a lot more shielded than this electron is. And that makes it a lot easier to remove because there's more repulsion forces from these other electrons pushing away on that electron, and so this electron would be easier to be removed from that atom and go and bond with something else. And when electrons leave and when they come and attach to other atoms, whenever electrons are moving, you typically have chemical reactions, right? And potassium is a lot more reactive than sodium because that outside electron is so much easier to remove than sodium's outside electron.